basically, and I want to discuss the Isle of Man because presumably we're bringing that back. So Jose Gonzalez made some claims that flat earthers are not doing observations and that they are not actually trying to figure out things in this world, and they're making the assumption that the earth is flat instead of actually trying to figure out its shape. Because most of them will say, I don't know what the shape of the earth is, or they will say, I know it's not a sphere, which is a very decisive claim if you ask me. Not knowing the shape is fine. Being zetetic about your knowledge is fine. But, well, okay, maybe it's not fine. I would prefer it over the somewhat dishonest position that they know the earth is not a sphere, which, how can you know it's not a sphere, for one thing? But it just seems like a dishonest position to begin with. In particular, I'm talking about a YouTuber named Anthony Riley. And he has a very long history of not necessarily being honest about his position. So I'm just going to go through one of his observations, and we're going to compare it to a model of the Isle of Man that I made with my ray tracing software. And I want to talk specifically about how to make his observation work on a flat Earth, because that's his claim, that this observation is perfectly consistent with, is inconsistent with the globe and consistent with the flat Earth. And the excuses that have been made as for why, well, as we shall see, land is actually missing, being obstructed by the horizon, is because of optical effects, and I want to discuss that optical effect. So I made this PNG here where it basically has side-by-side comparison of my 3 different models, and if you look, you can see I have the entire Isle of Man. Here's the flat Earth with standard refraction, aka the standard atmosphere. Here's the flat Earth refraction model, which I explicitly made to match the observation. And then here's the spherical Earth refraction plus, now for the first time I'm actually going to talk about miraging in the context of land masses like this. So let's first go over the flat Earth model and how it actually fails to predict what is actually happening in this observation. So one thing that you'll notice is that I tried to line these up as best as I could scale-wise. It's not perfect, but it's pretty damn close. It might be a little bit off, but no matter how much scaling I get, I'm still going to have issues. I should be seeing all of this land over here. And this is just not obvious in the picture. Second thing you'll notice, this land on this side, which is visible, is all of it is not hidden. It's all there. And we're seeing bits of land which should not even be seen, which should be seen on a flat Earth but are not seen in the image. I'm just going to scrub through this real quick and just point out some of the features. So there's this piece of land here, and of course this piece of land was supposedly hidden by atmosphere in the distance, right? That was the claim made by Nathan Oakley and co. When their I guess Galileo flat Earth Chris Monk-Seeley modeled out the Isle of Man, and his model actually looked very much so like this, because he was doing it on a flat Earth. So he had to basically cut this off arbitrarily, Chris Monk, which doesn't make, well, I mean, it kind of makes sense. I can kind of see how it's the atmosphere doing this, but when it's something where it is such a sharp cutoff, where like it's really just at a particular distance, I no longer render the image, that doesn't quite make sense. So that's one issue. This looks fine. This is stuff which is closer to the observer, so it seems to match decently well. There are some discrepancies. So in other images, you'll see you'll see a clear view of the top of North Barul and Snaefell, and you'll actually see that Snaefell is below North Barul, and this is confirmed by observations. Oh, by the way, I forgot to mention, this is Anthony Riley's second shot of the Isle of Man. The first one is from a different location, but this one is well established, the location and the elevation and all that stuff. So I'm using all of that information to render this image on a flat Earth and a round Earth. So basically what you have here is you have this little bump here, which seems to be showing more bump than what is necessary. The reason for that is because there's no cumulative drop. And then there's that little hill, right? This whole thing. So this whole thing looks decently well, but then we get to an issue when you reach this point. And basically this entire part of the island where my mouse is should be underwater, according to the flat Earth. Well, and what we'll actually figure out is how we can actually get that to happen. Right, so then we get to the floaty land over here, which lines up with this bit of the island here. So I know there was a debate actually of whether or not this is Isle of Man or not. This basically proves it. This is definitely the Isle of Man. And so we went from it being Scotland or Ireland to being Scotland to now the claim is that this bit of land is impossible to see on a globe. And the problem with that claim is that, one, it's excluding refraction, and two, it's based on a lie on how high Anthony Riley's observation point actually was. So let's go to my flat Earth model of refraction. So you can see automatically we're doing a lot better than before. Basically, what I've done is I've made refraction which sinks the entire island into the sea, or makes the islands appear to sink in the distance. And I've done a video about this in the past, but I just wanted to discuss now in this video kind of how much refraction is required to make this thing sink into the water. And basically the point is going to be very simple. People complain that we see things because it's there. That's been the argument by Nathan Oakley and crew, that there's optical effects, but most of the time we see things because they're there. And my point is basically going to be this. We don't see things because we were there on a flat Earth. We see things because we see things sunk into the ocean. And so if you want to argue that it's a ridiculous position that refraction is bringing stuff around the curve, I'm going to make you look like just as silly when you're talking about optical effects, because the optical effects are making things appear where they are not in reality on both models. The difference will be in the flat Earth model, it's going to be much more than what it is on the globe Earth. And I'm going to prove that. Okay, so going through this, you can already see it looks much better. I did not put an inferior mirage here, just to give you guys a sense of what sinking actually looks like. But yeah, it basically matches, not exact, but it's really close. It definitely is much better than the standard refraction. So at least now we know what temperature profile or what atmospheric conditions would make this sinking happen on a flat Earth. And we have something where it actually matches observations, which is good, which is what we've been asking for flat earthers to do for a very long time now. Now, in the case of when we don't have this inferior mirage, we actually get this little bump of land here because what happens is when you include the inferior mirage, as you'll see on the spherical model, this little bit goes away. It kind of gets covered up by the inferior mirage, but it's only this little sliver of land which is getting covered up. And basically there's a little bit of issue of alignment here. I did not make this composite, but it's pretty close. And the reason why it's not exact is because there's basically no landmarks here to go against. You're basically just trying to match up the clouds, which is very difficult. Okay, finally we have the round Earth, the spherical Earth model with refraction. And the refraction is not perfect, I will say. I spent a long time trying to, not a long time, I guess, a long time ago, I tried to build an inferior mirage which would actually match what we see here. I did some updates to my code, and it seems like it might have done something with the actual profile. So it's not a perfect match, obviously, but it does give most of the major features that we expect. And it basically matches the same as the flat Earth. So what this was basically a combination of standard refraction plus an inferior mirage to get things like the nose cone, where this thing kind of goes back under itself, and the floaty land. So basically, yes, I can model the floating lands very easily. It's not a big deal whatsoever. It's a very simple atmospheric profile which gave this effect. So now that I've gone through the different models, let's actually go through how much refraction there is. And how I'm going to measure refraction is I'm going to use the drop. So let's actually open up Inkscape. So basically what I'm doing is on a spherical Earth, we have a geometric drop, which most people know about. So what we have is as I go off into the distance, things are going to fall behind the curvature, which means that if I can measure this distance using a theodolite or something like that, I can get what is called the drop. Now, what happens is this drop actually increases with distance. And so what I've basically done is I've designed a refraction protocol, or a refraction model, atmospheric model, which actually gives the correct amount of apparent drop. Now, I say apparent drop because in reality, what happens is there is actually refraction. Ah, jeez. There's actually refraction which causes light to bend down. Sorry, guys. Jesus. Alright, how do I get this to work? Alright, fuck it. What happens is there's basically refraction which causes light to bend down like this, ever so slightly. And so what I can do is I can actually use the distance between this line, which is the curved line due to refraction, to calculate the drop. And basically what I want to do is I want to quantify the amount of drop between the geometric horizon, or the geometric drop, and the refracted drop. So there's going to be a certain amount of refraction that happens, and it's going to give a different value for the drop, because I measure the drop from the distance between the ray here and the surface of the Earth. And similarly for flat Earth, Oh, damn it. See, that's what I wanted to actually do. For a flat Earth, basically what I have is that there is no drop. So for any observer, I have no drop as a function of distance. But what I can get is I can get you know what? I'm really bad at this. I can get something like this. So how do I get this increasing drop as I go into the distance? What I need is I need to have a light ray which gets bent up in the distance. And this is what I've modeled basically on a flat Earth. And this causes things to sink into the distance. Now, again, I've done a video about this and basically shown that this amount of refraction is basically impossible on particular scales. But what I'm going to do is I'm going to basically make it quantitative. So tell basically what is the amount of temperature gradient required to get this refraction. Okay, so this is basically what I'm measuring. So the drop relative to the surface of the Earth for each light ray. All right, so just to start off with, here's the spherical Earth. So when I have no refraction, I get something like the red line. So as I go off into the distance, the amount of drop increases, the vertical drop. And this makes sense, right, because the ground is curving away from us. Now what happens is when I add refraction, that drop becomes slightly less because the refraction makes light get bent downward because of the density gradient being negative. Now on a flat Earth, I have a different picture. Now I still have, with my refraction model, I need to have the drop increase with distance. But when I have no refraction, there is no drop. So basically I should see, if the atmosphere was such that there's absolutely no refraction that day, then I should see no drop at all. Basically I should be able to see down to the bottom. So this was, and it gets even worse because in standard refraction, the drop actually decreases with distance. The light rays get bent down towards the surface of the Earth. And just to give you a comparison, here are the two models for refraction on a sphere and flat Earth, and these give almost matching results for the drop as expected. And they also give matching predictions in terms of the ray trace model, which is exactly what we want to have. So this is indeed indeed reflects reality because it gives us the exact it gives us almost an exact match with what we observe in reality. So this is how much refraction is required on a spherical Earth and on a flat Earth. So finally, let's come to what is the difference between the two. So what I did is I took the refraction drop minus the geometric drop. And what this gives us a measure for is how much refraction is actually doing. So in the sphere, we have at about 60 kilometers, we have minus 50 meters of drop missing, geometric drop missing, which seems like a lot, but it's over 60 kilometers. So the distances this is a very, very, very small angle. Now, that's not to say it's not small on a flat Earth, right? But the difference is about a factor of 5. Okay, if I'm being honest, maybe it's close to 4.5 times larger than the spherical Earth, and it's in the opposite direction. And the opposite direction is actually the key point. So because it's actually in the opposite directions, what that means is that the the temperature gradients are going to have to be so strong that they're basically not going to be able to be observed on Earth. And how strong does it have to be? Well, it's a good question. So let's close that. So here are the two atmospheric profiles to get those two effects. So I'm just going to be nice to the flat Earth, and I'm going to say that I'm going to make it this 2 degrees at 100 meters. So what that tells us is we have two, let's see, where's my calculator? So if I have my gradient so the degrees Celsius per meter is going to be 2 degrees minus the starting point, which is 15 degrees. So 15 minus 2 divided by 100. So it's about 0.13 degrees per meter. Now, the standard way of representing this temperature gradient is in degrees per kilometer. So if I want to change this in degrees per kilometer, what I do is I multiply this by 1,000, right? The units are, it's the degrees Celsius divided by meters. So if I multiply the top and the bottom, which doesn't change the actual number, if I multiply the top and the bottom, I'll get 0.13 times 1,000. It gives me 130 degrees Celsius per 1,000 kilometers, or 130 degrees Celsius per kilometer. In the case of the standard atmosphere, in this case I'm using the dry adiabatic lapse rate, I get 15 down to 14, so it is 1 degree divided by 100, which is about 0.1. So times 1,000 is about 10 degrees per kilometer, which is actually fairly steep. But this is, if you look up what the dry adiabatic lapse rate is, this is almost identical to that. So atmospheric lapse rate. All right, so let's just go to Wikipedia real quick. So the lapse rate is basically how fast the temperature changes. And in the case of a dry atmosphere, you get a lapse rate of about 9.8 Celsius per kilometer, which is what I used in that calculation, the standard lapse rate. So this is what it says. So the dry adiabatic lapse rate is 9.8. The moist adiabatic lapse rate varies strongly with temperature. A typical varies around 5 degrees Celsius per kilometer. And I think the average value is 6.5, if I'm not mistaken. Atmospheric lapse rate. So, okay, so it averages at about 6.5 degrees Celsius, right? So, to get a flat Earth to look like it's a sphere, which that's obviously what it looks like if we compare the models, we need to have a lapse rate which is about, let's see, it's 130, so it's 130 divided by 6.5. We need to have a lapse rate which is 20 times the average lapse rate every single day. So this should automatically show that there's a contradiction, because the average is nowhere near what is required to actually get the refraction that would be required to get obstruction on a flat Earth. So basically, we're at an impasse here, guys. Either all of optics is wrong, and all of all of fluid dynamics is wrong, or the Earth is not flat. That's basically the end of the story here. So I would like to finally thank Anthony Riley for his beautiful observation of the Isle of Man, which not only shows very good evidence that the Earth is a sphere, but also disproves that the Earth is actually flat. Just give Anthony Riley a big old round of applause for me. And I will actually post a link to this image in the description, so you guys can actually go ahead and tout this around and point people back to this video, just to maybe wake up a few flat earthers, because right now they're living in a fantasy world. All right, that is basically all I have for today. Thank you very much for stopping by. I will talk to you guys later.